Today we will be studying interpolation in numerical analysis. By interpolation we mean the insertion of something of a different nature into something else. But in mathematics we know the insertion of an immediate value or term into a series by estimating or calculating it from surrounding known values. Suppose you are having the knowledge of values of a function at some particular points. Suppose a function is known only at the points, this is our x-axis and this is y-axis. The values of the function are known at the points x0, y0, at the point x1, y1, at the point x2, y2, and so on. And I wish to know the value of the function at some other point based on the known values of the function. So what can I do? I can just add the points like this. If there are some other points, then I can extend it in that manner. And if I wish to know the value of the function at some other points, say I am willing to know the value at some points, say x dash. So then I will take the ordinate here and this will be the value of the function. This is one way. But what we have taken here as the function itself consisting of these straight lines, and you know at this point x1, y1 there is a sharp edge. If there is a sharp edge, the function will not be differentiable at that point, although it is continuous there. So if we can find or if we can estimate a function which will be smooth, means a function of this kind, then we will be able to find the derivative of that function at any point. And for that purpose, polynomials are the best choices. Polynomials are the best choices because polynomials are continuous everywhere, differentiable everywhere, integrable everywhere, and other many nice properties of polynomials are there. So what a polynomial is? A polynomial is an expression of the form ai x to the power I ranges from 0 to some fixed integer k. I can write it as px. That is, if a function of x is linear combination of different powers of x, linear combination of different powers of x, x square, x cube, x to the power k, and constant is x to the power 0, that is 1, and these are the coefficients when we take the linear combination. That's a polynomial. And one thing to be reminded, that the polynomial will have finite number of terms. Another thing is that if p1x is a polynomial and p2x is another polynomial, and we take their linear combinations c1 p1x plus c2 p2x, where c1 c2 are real numbers, then px equals to c1 p1x plus c2 p2x is also a polynomial. If p1x and p2x are polynomials. By degree of a polynomial, we mean the highest degree of x present in the expression. So when we are adding two polynomials, or when we are taking the linear combination of two polynomials, then the degree of the sum polynomial will be the degree of the highest degree polynomial. So we will start with Lagrange's interpolation formula. Suppose the function y is known at the points x0, x1, xn, where the values are y0, y1, yn. At these n plus 1 points, y is known, and based on this knowledge of the value of y, you will have to find the value of y at some other points ranging between x0 to xn. Rather, we will find a polynomial of degree not exceeding n, which will have the same values of the function y at the given points x0, x1, xn. That is, we will find a polynomial phi x, or better we take Lx, Lagrange's interpolating polynomial. So we take it Lx is a polynomial of degree not exceeding n, such that Lxi is equals to yi at xi equals to x0, x1, xn. That is, I equals to 0, 1, 2 up to n. At these n plus 1 points, Lx will coincide with the value of the function y, that is y0, y1, yn will be the values of the polynomial Lx also at these points. Now in Lagrange's interpolation formula, Lx is taken as a linear combination of some other polynomials. Lix yi I equals to 0 to n, that is y0 L0x plus y1 L1x plus in this way yn ln x, where each of the functions L0x, L1x, ln x are all polynomials in x of degree not exceeding n. These are all polynomials of degree not exceeding n, and y0, y1, yn are all constants. So when we are considering the linear combination of these polynomials, that will also be a polynomial of degree not exceeding n. Now you see, if we choose the polynomials L0x, L1x, ln x in such a manner that L0 x0 will be 1 and all other Lix will be 0 at x0, then Lx0 equal to y0 will be satisfied. That is, here it is y0 and here y0 into something plus y1 into something, in this way yn into something, and we are choosing this one as 1, all are 0. That is, then it will be a valid relation. That is, if we choose L0x x0 equals to 1 and Lix0 equals to 0 for I equals to 1 to n, then Lx0 equal to y0 will be satisfied. Similarly, if we take, when we consider the value y1, that is L at x1, then we will take L1 at x1 as 1 and value of all other Lix at x1 as 0 for I equals to 0 to n. If it happens, then L at x1 will be equals to y1. In this way, if we choose ln xn equals to 1 and li xn equals to 0 for all I equals to 0, 1, 2, n minus 1, then we will get Lxn equals to yn. That is, if we choose Lix's in this manner, then our primary condition that the interpolating polynomial should be matching with the values y0, y1, yn at the points x0, x1, xn will be satisfied. So if we combine all these, we can write Lixi equals to 1, and Lixj equals to 0 for j equals to 0, 1, 2 up to I minus 1, then I plus 1, n. That is only at the point xi the value of Li will be 1, and at all other points it will be 0, and it has to be valid for all I. For all I, these two conditions are to be valid. Now, if we consider this thing, Lix is a polynomial in x which has the roots x0, x1, x2, xi minus 1, xi plus 1 up to xn. Then we can write, and how many terms, how many factors, linear factors we are getting? How many linear factors we are getting? X minus x0, x minus x1, in this way x minus xi minus 1, x minus xi plus 1, x minus xn. How many linear factors we are getting? 0 to n, that means n plus 1, and from there ith term is not there. So, in total we have n terms, n linear factors. So, when they are multiplied, that will give a polynomial of degree n itself. So, the Lix can be taken as some constant, suppose Ci times this one, because Lix becomes 0 at x0, at x1, at x2, xi minus 1, xi plus 1, xn. So, x minus x0 is a factor, x minus x1 is a factor, x minus xi minus 1 is a factor. In this way, x minus xn is a factor. So, all these are linear factors of Lix. When they are multiplied, we see the product itself becomes a polynomial of degree n. So, the polynomial Lix will be a constant multiple of all these linear factors, and these constant Cix can be determined from the other relation Lixi equals to 1. So, if you put x equal to xi in this relation, the last relation, if you put x equals to xi, then you get Lixi means 1 equals to Ci times xi minus x0, xi minus x1 up to xi minus xi minus 1, xi minus xi plus 1, xi minus xn. That is Ci equals to 1 by xi minus x0, xi minus x1, xi minus xi minus 1, xi minus xi plus 1, xi minus xn. Thus, Lix is x minus x0, x minus x1, x minus xi minus 1, x minus xi plus 1, x minus xn by xi minus x0, xi minus x1, xi minus xi minus 1, xi minus xi plus 1, xi minus xn. If we write it in product form using the product notation, we can write it product over I equals to 0 to better we write j equals to 0 to n x minus xj by xi minus xj, and the term j equal to I is not there. So, j not equals to I, and then finally we can write Lx equals to sum Lix yi I equals to 0 to n, that is equals to sum I equals to 0 to n product over j equals to 0 to n x minus xj by xi minus xj, j not equals to I times yi. So, that is the Lagrange's interpolation polynomial. It is our Lagrange's interpolating polynomial. It can be written in other ways also. If we choose a polynomial psi x equals to x minus x0, x minus x1, all the terms up to x minus xn, then what is psi dash x? If we differentiate the product of n plus 1 linear factors, then for the first term, if we differentiate, you will get 1, all the others will be there. Next, when we take the second term, its derivative is 1 and the others will remain as it is. In this way, the last term will be, for this one we have the derivative 1 and all others will remain same as it is, x minus x n minus 1. So, what is psi dash x I? In this product, x minus xi is there. So, when we put x equals to xi, this product term will become 0. In this product also x minus xi is there, it will become 0. Everyone will become 0 except one where x minus xi term is not there. And so, when we are putting x equals to xi, only that term will remain there, and that value will be xi minus x0, xi minus x1, xi minus xi minus 1, xi minus xi plus 1, xi minus xn. That is the term obtained for differentiating the factor x minus xi, and remaining the others, keeping all others as it is. Only that term will be non-zero for x equals to xi, and all other terms will be 0. And you see, this is nothing but the terms here. This term, and the numerator is psi x by x minus xi. Only the term x minus xi is not there, all other terms are there in the numerator. So, for the numerator it is psi x by x minus xi, and in the denominator we have psi dash xi. So, using these notations, using the notation of psi x, we can have Lix equals to psi x by x minus xi, and in the denominator there will be psi dash xi. Thus, Lx equals to sum I equals to 0 to n psi x by x minus xi into psi dash xi times yi. This is another form of Lagrange's interpolating polynomial. So, if we consider a small problem, suppose for x values x0, x1, x2, x3, the y values y0, y1, y2, y3. Only these 4 points are known to us. Then what will be the Lagrange's interpolating polynomial? Lagrange's interpolating polynomial will be given by Lx equals to x minus x1, x minus x2, x minus x3 by x0 minus x1, x0 minus x2, x0 minus x3 y0 plus x minus x0, x minus x2, omitting the term x minus x1 this time, x minus x3 by x1 minus x0, x1 minus x2, x1 minus x3 y1 plus x minus x0 into x minus x1 into x minus x3 by x2 minus x0, x2 minus x1, x2 minus x3, y2 plus x minus x0, x minus x1, x minus x2 by x3 minus x0, x3 minus x1, x3 minus x2 into y3. Here you see each of the terms is a product of 3 linear factors of x. So, each one is a polynomial of degree 3, and it is very easy to remember because the terms are very much similar. In the first one we have omitted x minus x0, and the denominator is obtained by putting the x value x0. The constant coefficient is y0. In the second term we have omitted x minus x1, and in the denominator x is replaced by x1. Similarly for the other two terms. Okay, let's take a numerical example with 4 points, only. Suppose at x equals to x0, x equals to 0, y value is given by 2.5. At x equals to 2, it is given by 3. At x equals to 3, it is given by 4.5, and at 4 it is given by 6. Suppose these 4 values of y are known, and based on these 4 values we will find the Lagrange's interpolating polynomial, which will be matching with those values 2.5, 3, 4.5 and 6 at the point 0, 2, 3, 4. So, if we put the values of x0, x1, x2, x3 and y0, y1, y2, y3 just in the above expression, then we will have Lx equals to x minus 2 into x minus 3 into x minus 4 by minus 2 into minus 3 into minus 4 into 2.5 plus x minus 0, that is x, into x minus 3 into x minus 4 by two minus 0 is 2, 2 minus 3 is minus 1, and 2 minus 4 is minus 2 times 3 plus x minus x0 is 0, x minus 2 into x minus 4 by 3 minus 0 is 3, 3 minus 2 is 1, and 3 minus 4 is minus 1 times 4.5, and the last term is given by x into x minus 2 into x minus 3 by 4 minus 0 is 4, 4 minus 2 is 2, 4 minus 3 is 1 times 6. That is minus 1 by 24 x minus 2 into x square minus 7x plus 12 into 2.5 plus 3 by 4 into x cube minus 7x square plus 12x plus minus 4.5 by 3 is 1.5 into x cube minus 6x square plus 8x, and the last one is 3 by 4, that is 0.75 into x cube minus 5x square plus 6x. So the first one gives 2.5 by 24 is what? 2.5 by 24 is minus 0.1042 into x cube minus, if you multiply x with minus 7x, it gives you minus 7x square minus 2x square, so minus 9x square plus 14x plus 12x, that is 26x minus 24. So we could keep it in fractional form also, no harm. I can write it as 5 by 48 plus 3 by 4 into x cube minus 7x square plus 12x minus 3 by 2 into x cube minus 6x square plus 8x plus 3 by 4 into x cube minus 7x square plus 12x. No, sorry, x cube minus 5x square plus 6x, this one. So finally what we have, 3 by 4 x cube plus 3 by 4 x cube is 3y2 x cube minus 3y2 x cube cancelled out, minus 5 by 48 x cube, and what are the square terms? It is minus 21 by 4 okay, let me do one step more. 45 by 48 minus 21 by 4 plus 9 minus 15 by 4. So 21 by 4 minus 15 by 4 is minus 9 and is plus 9. So these three cancel out, x square, and the coefficient of x, it will be minus 65 by 24, and from here 9, from here minus 12, and from the last one it will be 9 by 2x, and the constant term will be from the first expression, so it will be plus 5 by 2. That is minus 5 by 48 x cube plus 15 by 16 x square. It is what? Minus 3 plus 9 by 2. So minus 3 plus 4 and half. So it is 1 and half. That is 3 by 2. 3 by 2 means 36 by 24 minus 65 by 24. So it will be minus 29 by 24x plus 5 by 2. I do not know if I have calculated correctly. If there is anything wrong in calculation, you need to rectify those, but that's the procedure how we have to find the Lagrange's interpolating polynomial. One thing you can see easily, that at x equals to 0, the value is 5 by 2, that is 2.5. You can check the other values also if those are matching with the tabulated values. Now, one thing you may note, these differences. x0 was 0, x1 was 2, x2 was 3, and x3 was 4. The difference between x1 and x0 was not same as x2 and x1. That is, the points where the values of y are tabulated are not equally spaced. But if they are equally spaced, then the Lagrange's interpolating polynomial can have some simpler form. In that case, for equally spaced points, that is x0, x1, xn, they are all equally spaced. The space between two successive points are same, that is x1 minus x0 is same as x2 minus x1, that is again same as x3 minus x2, and this way xn minus 1. Suppose this step length, that is the difference between two successive points, is h. So what we can write? We can write xi minus xi minus 1 equals to h for all I. For all I equals to 1 to n. We are not taking I equal to 0 here because 0 minus 1 x minus 1 is not defined. And then we can have all the points xi's in terms of x0 and h, because x1 minus x0 is h, so x1 is given by x0 plus h. x2 can be given by x1 plus h, that is x0 plus twice h. In this way, what will be your xi? Xi will be x0 plus ih, and this is valid for I equal to 0, 1 up to n. And we introduce a new variable s to make the form of the polynomial simpler. Which is given by x minus x0 by h. Why I am taking it in this way? Because it will replicate this one. If you take x equals to x0 plus sh, where s is a variable, then s is given by x minus x0 by h. So what we will have now? What about x minus xi? X is x0 plus sh and xi is x0 plus ih. So we have x minus xi, s minus ih for I equals to 0, 1 up to n. So what is Lix then? Lix was product j equals to 0 to n, j not equals to y, x minus xj by xi minus xj times yi. So we need to calculate xi minus xj also. It is also not difficult. Xi minus xj equal to x0 plus ih minus x0 plus jh, that is equals to I minus j times h for all I and j. So it can be written as product j equals to 0 to n, j not equals to I, s minus j times h by I minus j times h yi, and here no x is there, so li s, then h will cancel out both from numerator and denominator, and finally L will also be a polynomial in S, then that will be given by sum I equals to 0 to n, product over j equals to 0 to n, j not equals to I, s minus sj by I minus j times yi. So that's the expression for Lagrange's interpolating polynomial when the points where the values of y are tabulated are equally spaced. Now for equally spaced points, we will learn Newton's forward difference interpolation formula. Or sometimes it is called Newton's forward interpolation formula. As before, for the x values x0, x1, x2 up to xn, the values of y are y0, y1, y2, yn. Only these n plus 1 values of y are known at the points x0, x1, x2, xn, and from there we have to construct a polynomial of degree less than equal to n, which will match with the values y0, y1, y2, yn at the given points x0, x1, x2, xn. Here we consider the polynomial in a bit different way. Suppose we take the polynomial phi x, the interpolating polynomial, in this form a0 plus a1 into x minus x0 plus a2 x minus x0 into x minus x1 plus a3 x minus x0 x minus x1 x minus x2, in this way up to a n x minus x0 x minus x1 up to x minus xn minus 1. And here the points x0, x1, x2 are equally spaced, means the difference between x0, x1, x1, x2, x2, x3 are all same. Suppose that spacing is h, that is x1 equals to x0 plus h, x2 equals to x1 plus h, in this way xn equal to xn minus 1 plus h, and thus we will have xi equals to x0 plus ih for I equals to 0, 1, 2, n. Now we have at x equal to x0, phi x should match with the value y0, that is at x equals to x0 phi x equals to y0. Then we will have, if we take the definition of the polynomial how we have constructed it as equation number 1, then at x equal to x0 phi x equal to y0 gives y0 equals to a0 and all other terms will become 0 as x minus x0 is a linear factor in every term. Then at x equals to x1 we have from 1 y1 equals to a0 plus a1 times x1 minus x0, and all other terms will vanish because in all other terms x minus x1 is a factor, so each term will be multiplied with 0 and will vanish. We will have only this thing. Already we know the value of a0 as y0, so from here we get a1 equals to y1 minus y0 by x1 minus x0. And we know x1 minus x0 is h, and this thing y1 minus y0, this difference is called forward difference of first order and is denoted by delta y0. Similarly, y2 minus y1 will be denoted by delta y1, and in general yi minus yi minus 1 is denoted by delta yi minus 1. We can also have differences of higher orders. If we consider the difference between delta y1 and delta y0, that will be second order difference delta to y0, that is delta to y0 equals to delta y1 minus delta y0. In this way we can have delta to yi equals to delta yi minus delta yi minus 1. Similarly, we can have higher order differences. So a1 can be written as delta y0 by h. Again, at x equals to x2, we will have from equation 1 y2 equals to a0 plus a1 times x2 minus x0 plus a2 times x2 minus x0 into x2 minus x1, and all other terms will vanish because x minus x2 is a factor in all other terms. So we have y2 equals to a0 is y0, a1 is delta y0 by h, x2 minus x0 is twice h, plus a2 times x2 minus x0, that is twice h, into x2 minus x1 is h. That is a2 equals to y2 minus y0 minus 2 delta y0 whole by twice h square. If we expand, we will have y2 minus y0 minus 2y1 plus 2y0 by 2h square equals to y2 minus 2y1 plus y0 by twice h square. Now this can again be written as y2 minus y1 minus y1 minus y0 . The first one within the first parenthesis is delta y1 minus delta y0 by twice h square equals to delta 2y0 by twice h square. In this way, if we proceed, we will see a3 equals to delta 3y0 by 3 factorial h cube, and an will become delta ny0 by n factorial h to the power n. Thus finally we will have the polynomial phi x equals to y0 plus x minus x0 times delta y0 by h plus x minus x0 into x minus x1 by twice h square delta 2y0 plus x minus x0 x minus x1 into x minus x2 by 3 factorial h cube delta 3y0. In this way, the last term will be x minus x0 x minus x1 up to x minus xn minus 1 by n factorial h to the power n delta n y0. So that's the Lagrange's forward interpolation polynomial. As before, if we introduce another variable s, where s is given by x minus x0 by h, then x minus xi will be x minus x0 minus xi minus x0, that is equals to sh minus ih, that is equals to s minus I times h for I equal to 0, 1 to n. Thus, in terms of s, we can have the polynomial phi as delta y0 plus s delta y0, sorry, the first one is only y0, plus s delta y0 plus s into s minus 1 by 2 delta 2 y0 plus s into s minus 1 into s minus 2 by 3 factorial delta 3y0. In this way, the last term will be s into s minus 1, s minus 2, s minus n minus 1 by n factorial s minus n minus 1, this one, or we can write s minus n plus 1 by n factorial delta n y0. That is the Newton's forward difference interpolation formula. Now, how to find the values of the differences of different orders? That can be done in a mechanical way if we write them in a table. Suppose that x equals to 0, 1, 2, 3 and 4, the y values are suppose 10, 25, 37, 48, 62. Then the first order differences will be 25 minus 10, 15, we will write in the middle. 37 minus 25, 12, we will write them in between 2 and 1. It is 11 and it is 14. Next, the second order differences, it will be 3 minus 1, 3. Then the third order differences, minus 4, 4, and the fourth order difference will be given by 8. Obviously, this one is delta y0, that is delta 2y0, delta 3y0 and delta 4y0. That is, if we take the elements in the top diagonal, those will be our coefficients, this thing. So, for these given values of x and y, if we wish to find the Newton's forward interpolation polynomial, that will be given by phi s equals to 10 plus s into 15 plus s into s minus 1 by 2 into 3 plus s into s minus 1 into s minus 2 by 3 factorial means 6 into minus 4 plus s into s minus 1 into s minus 2 into s minus 3 by 4 factorial, that is 24 into 8, and simplifying this one you will get the required polynomial. And finally, we will learn Newton's backward difference interpolation formula. Here we choose the polynomial phi as yn plus an x minus xn plus an minus 1 x into xn into x minus xn minus 1 in this way, a1 oh yes, like the forward difference formula, we will start from a constant term, not yn. This is n, this is a n minus 1, a n minus 2. So the last term will be a0, x minus xn, x minus xn minus 1, and this way up to x minus x1. Since phi x will match with the values of y at the given points x0, x1, xn, for x equals to xn we will have the value of phi x as yn equals to an plus all other terms will be 0 because x minus xn is a factor in each of the terms. For x equals to xn minus 1 we have yn minus 1 equals to an plus an minus 1 into xn minus 1 minus xn, and all other terms will become 0 because x minus xn minus 1 is a factor in each of the remaining terms. We already know the value of an, thus we have an minus 1 equals to yn minus 1 minus yn by xn minus 1 minus xn, that is an minus 1 equals to, if we multiply the denominator and numerator both by minus 1, yn minus 1 by xn minus xn minus 1. The thing on the top is known as backward difference of yn. It is read as nabla yn equals to yn minus 1, and xn minus xn minus 1 is h. For x equals to xn minus 2 we have yn minus 2 equals to an plus an minus 1 into xn minus 2 minus xn plus an minus 2 xn minus 2 minus xn into xn minus 2 minus xn minus 1, and all other terms will be 0 because x minus xn minus 1 xn minus 2 will be factors in each of the remaining terms. If we simplify and use the values of an and an minus 1, we will get an minus 2 equals to nabla 2 yn by twice h square as earlier. In this way, if we go on, we will finally get a0 equals to delta n yn by n factorial h to the power n. Thus we have phi x equals to yn plus x minus xn by h nabla yn plus x minus xn into x minus xn minus 1 by h square twice h square delta 2 yn. Next term will be x minus xn, x minus xn minus 1, x minus xn minus 2 by 3 factorial h cube nabla 3 yn. In this way, the last term will be x minus xn, x minus xn minus 1 to x minus x1 by n factorial h to the power n nabla n yn. As before, if we use another variable, say t equals to x minus xn by h, then we will have x minus xi equals to x minus xn minus xi minus xn. X minus xn is th, and what is xi minus xn? Or rather xn minus xi, xn minus xi, xn is x0 plus nh, we have seen earlier, and xi is x0 plus ih, so it will be n minus ih. So xi minus xn will be I minus n h. That is equals to t minus, or I can write better, n plus t minus I times h. If we use that variable t, we will finally get phi as a polynomial of t, which will be given by yn plus x minus xn is th, x minus xn by h is t, so it is t times nabla yn plus t times t plus 1 by 2 nabla 2 in x minus x n minus 1, put the value of I as n minus 1, you will get n plus t minus n minus 1, that is equals to t plus 1. So if you use here t into t plus 1 by 2 delta 2 in, the next term will be t into t plus 1 into t plus 2 by 3 factorial nabla 3 yn. In this way the last term will be t into t plus 1 into t plus 2 by and the last term will be t plus n minus 1. I is 1 then by n factorial delta n yn, and that's the Newton's backward difference interpolation formula. Now the question is, when we will use which formula? It is clear that if the tabulated points are not equally spaced, then we will not be able to use Newton's formulas, neither the forward difference formula nor the backward difference formula. If the data points are not equally spaced, then we have the only one option to use the Lagrange's interpolation formula, and if the points are equally spaced, then we will choose Newton's forward difference formula if we are asked to find the value of the value of the function near the beginning of the table. Suppose here the y values are known at the points x0 equal to 0, x1 equal to 1, x2 equals to 2, x3 equals to 3 and x4 equals to 4, and if I have been asked to find the value of y at the point 0.5, that is near the beginning of the table, then we will use Newton's forward difference formula. And if we are asked to find the value of the function near the end of the table, suppose if I have been asked to find the value of y at 3.7, that is near the end of the table, then we will use Newton's backward difference interpolation formula. And if they are equally if the data points are equally spaced, then also we will use the Lagrange's interpolation formula, but the Newton's or backward forward or backward difference interpolation formula will be more suitable when the data points are equally spaced. And one thing, near the beginning of the table means if you are asked to find the value at minus 0.1, then it will be called extrapolation, not interpolation. It will be called extrapolation, that is the value has been asked outside the range where the values are known. There are several methods to extrapolate the values. For the time being, we are concerned with interpolation only. So just remember that for unequally spaced data points, we will use Lagrange's. For equally spaced points near the beginning of the table, we will use Newton's forward difference formula, and for equally spaced points near the end of the table, we will use Newton backward difference interpolation formula. So that's all for today. Thank you all.